Now, let's spend some time on how you can differentiate yourself as a developer. Most developers approach coding interviews by memorizing solutions to hundreds of problems. But here's the reality. You don't need to memorize hundreds of solutions. You need to recognize 3 patterns. Let's take a classic problem. Finding 2 numbers in an array that add up to a target. The brute force approach uses nested loops, checking every possible pair. That's order n squared. Operations. Slow, inefficient, and exactly what gets you rejected in interviews. But watch what happens when you recognize this as a 2-pointer problem. 2 cursors moving inward from opposite ends, eliminating impossible pairs with each step. Suddenly it's order n. 1 pass. Done. The difference isn't intelligence or experience. It's pattern recognition. This specific problem, a common interview challenge known as 2-sum, serves as our initial illustration to demonstrate how applying the right pattern can dramatically improve efficiency. Here, we visually trace the brute force method in action. Observe how it systematically checks every single combination, resulting in a high number of operations and demonstrating the inherent inefficiency of quadratic time complexity. Now, observe the 2-pointer approach. By leveraging a sorted array, pointers move inward, intelligently eliminating entire sections of the search space with each comparison. This strategic movement drastically reduces operations, achieving a linear time complexity and quickly finding the target sum. This efficiency is a hallmark of pattern-based problem solving. In fact, 3 core patterns, 2 pointers, hashing, and stacks, form the foundation for solving a vast number of coding challenges. Indeed, these 3 patterns alone provide a solution framework for approximately 60% of all LeetCode problems, demonstrating their universal applicability and power. Mastering these patterns means you can approach even complex problems with confidence. It's not about rote memorization, but about developing the intuition to see the underlying structure of a problem and select the most appropriate tool to solve it quickly and efficiently. By the end of this video, you'll possess a robust decision framework that can dramatically reduce your problem-solving time. Let's begin by deeply understanding what makes these patterns so powerful. Let's start with 2 pointers, the pattern that turns nested loops into single passes. The core intuition is simple. Instead of checking every possible pair with 2 nested loops, use 2 cursors that move intelligently through the data. Here's the key insight. When your input is sorted, you can eliminate entire ranges of possibilities with each comparison. This means that for a sorted list, if the current pair doesn't meet your condition, you can confidently discard one of the pointers, narrowing your search space. This intelligent movement is what gives the 2 pointers pattern its efficiency. This efficiency is why 2 pointers is so powerful. A traditional nested loop approach, often represented as O of n squared, performs many redundant checks. But by intelligently moving 2 pointers, you reduce the problem to a single pass, achieving O of n complexity. For n equals 100, this means the difference between nearly 4,950 operations versus just 100. This is a massive performance gain for your algorithms. Now, let's watch this in action with a classic example. The container with most water problem. Here, you're given an array of heights representing vertical lines. Your goal is to find 2 lines that, along with the x-axis, form a container that can hold the most water. To apply the 2 pointers pattern, we start by placing one pointer at the extreme left and the other at the extreme right. This gives us the maximum possible width for our container. We then calculate the area formed by these 2 lines, limited by the height of the shorter line. Now, here's the crucial decision rule for this problem. Always move the pointer that is currently at the shorter line inward. This is because moving the taller pointer can only decrease the width, and since the height is limited by the shorter line, it can never improve the calculated area. Moving the shorter pointer, however, offers the possibility of finding a new, taller line, potentially increasing the overall height of the container even as the width decreases. This is a greedy strategy that guarantees optimality. This process continues, always strategically moving the pointer corresponding to the shorter line. With each step, we re-evaluate the area and update our current maximum if a larger container is found. This systematic approach ensures we explore all relevant possibilities while efficiently converging on the optimal solution. This is the true power of the two pointers approach. Each time we move a pointer, we're not just checking one pair. We're effectively eliminating an entire class of configurations involving that particular line at its current width. This dramatically prunes the search space and is the fundamental reason for its efficiency. So, when should you reach for the two pointers pattern? First, if your data is sorted or can be sorted efficiently, it's a strong candidate. Second, if the problem involves finding pairs, subsequences, or requires comparisons between elements. And finally, if you need to optimize and avoid the performance overhead of nested loops. The signature to look for is when the problem asks about pairs, subsequences, or comparisons, and the data is sorted or can be sorted cheaply. Classic examples include toSum on a sorted array, valid palindrome, and, as we just saw, container with most water. When you recognize this signature, two pointers is almost always the right tool to apply for an efficient solution. Now let's look at hashing. The pattern that trades memory for speed. The core intuition. Instead of searching through data repeatedly, store it in a structure that gives you instant lookups. Hash tables let you check, have I seen this value before? In constant time, instead of linear time. That transforms order n squared problems into order n. The trade-off is clear. You're using extra memory to eliminate redundant comparisons. When space isn't the bottleneck, hashing is almost always the right choice for lookup-heavy problems. Here's a perfect example. The contains duplicate problem. Given an array, return true if any value appears twice. The naive approach uses nested loops. For each element, scan the rest of the array to see if it appears again. That's order n squared. But watch what happens with hashing. Create an empty hash set. Iterate through the array once. For each element, check if it's already in the set. If yes, you found a duplicate, return true. If no, add it to the set and continue. Single pass. Order n time, order n space. The signature for hashing. The problem asks, have I seen this, count occurrences, or find complements? Anytime you need fast lookups or membership testing, hashing is your tool. Finally, let's look at stacks. The pattern for nested structures and matching pairs. The core intuition. Last in, first out ordering naturally matches closing elements to their most recent opening element. Stacks are perfect for problems involving hierarchies, brackets, or undo operations. The signature example is valid parentheses. Given a string of brackets, parentheses, square brackets, curly brackets. Determine if they're properly nested. The stack approach is elegant. Iterate through the string character by character. When you see an opening bracket, push it onto the stack. When you see a closing bracket, check if it matches the most recent opening bracket by popping from the stack. If they match, continue. If they don't match, or if the stack is empty when you need to pop, the string is invalid. At the end, if the stack is empty, all brackets were properly matched. If not, there are unmatched opening brackets. This works because the stack's last in first out property mirrors the nested structure of valid bracket sequences. The most recently opened bracket must be the first one closed. Stacks solve this in order n time with order n space. The signature to look for. Nested structures, matching pairs, or any problem where the most recent element matters. When you see that, reach for a stack. Each opening bracket is pushed onto the stack. At any moment, The top of the stack represents the most recent bracket that still needs a matching partner. Now we encounter a closing brace. The top of the stack contains the corresponding opening brace, so we have a valid match and can safely remove it. The final closing parenthesis matches the final opening parenthesis. After the pop operation, the stack is completely empty. We've reached the end of the string with no mismatches and no brackets left waiting to be closed. The sequence is valid. Here's the failure case. The top of the stack contains an opening square bracket, but the current character is a closing parenthesis. Since the pair doesn't match, we can immediately conclude the string is invalid. Notice that we stop immediately after finding the mismatch. There's no need to process the remaining characters because the nesting structure has already been broken. This timeline captures the evolution of the stack state as each character is processed. Every opening bracket grows the stack, and every matching closing bracket shrinks it. The reason stacks work is deeply tied to nesting. The most recently opened bracket is always the next one that must be closed, which is exactly the behavior provided by last-in, first-out ordering. Whenever you see nested structures, matching pairs, or a need to access the most recent item first, a stack should immediately come to mind. Valid parentheses is one of the classic stack problems. But the same pattern appears throughout compilers, expression evaluation, browser history, undo systems, and many other real-world applications. Now you've seen all three patterns. The final skill is knowing which one to choose before you write any code. This is where pattern recognition becomes a superpower. Let's build a decision framework. Start by reading the problem constraints carefully. They're hints, not just details. Is the input sorted? That's a signal for 2 pointers. Does the problem ask if you've seen a value before or need to count occurrences? That's hashing. Does it involve nested structures, matching pairs, or undo operations? That's a stack. Let's apply this framework to real problems. ToSum with sorted input. Sorted data plus pair. Finding equals 2 pointers. Contains duplicate. Membership testing equals hashing. Valid parentheses. Matching pairs equals stack. Merge sorted arrays. Sorted inputs plus sequence building equals 2 pointers. The pattern isn't hidden. It's in the problem structure. Once you recognize the signature, the implementation becomes straightforward. You're not guessing or memorizing hundreds of solutions. You're seeing the problem shape and choosing the proven tool. These 3 patterns, 2 pointers, hashing, stacks, are your foundation for solving 60% of coding interview problems. Master them, and you'll walk into any interview with confidence.